generation tools for how to assess ataxia in the context of clinical trials. Dr. Gupta is going to be joining us remotely, so we're really going to have like a full technological presentation. And if you'll get out your phones or your iPads, we're also going to do some polling questions during Dr. Gupta's session. So I'm going to turn it over now to Dr. Gupta. Thank you. Hi, Anupam.
Hi, Jen. Good to see you. Thank you for the introduction. I'm going to try to share my slides here. Okay, great. I think everyone can see. So I'm going to talk about our work in creating digital measures of movement in Friedreich's ataxia. And the goal is to both share where we are with digital measures and to understand the FA community's perspective on digital tools. Okay, so to get us started, I'm going to ask a few questions about devices that you already use at home. So if everybody can go onto Poll Everywhere and see if you can access this question and answer on your device. And I think the tech team is going to transfer to the real-time polling so that we can see answers as they come in. But please correct me if I'm wrong.
Yep. We can see the real-time responses.
Okay, so you can see them on your side.
Yes, can you see them?
Perfect. I cannot, but let me see if
I'll give you a quick rundown of where we are. So about 57% of people use a watch, and about 14% health app, small percentage other, and about 25% don't use any device at all.
Okay, perfect. Are answers still coming in, or should we move on to the next question?
I think we can move on. We've kind of settled in these percentages.
Okay, thank you. All right, so the next question is, what information do you track using your wearable device? Is it information about fitness, sleep, body temperature, heart rate, or something else?
And for this question, I think you can select as many as are applicable. You don't have to pick just one. One? Okay. So about 50% of people are indicating fitness, about 10% sleep, about 10 to 12% heart rate, and about 25% they're not tracking anything.
Okay, all right, so the majority of people are tracking something about their health on a wearable device. All right, so
Yep.
then the last question here at the beginning is, have you ever participated in FA research that uses a wearable device or other digital device to measure movement or health?
About 70, 30, 30% yes, a little under 30% yes, 70% no.
Okay, great. Jen, do we have numbers as well or just percentages?
Right now on the screen, I only have percentages, but
Okay,
we'll have the numbers later on.
great. Thank you.
Yep.
All right, so we'll move on. And when we talk about digital measures, there are two main ways that we measure movement. We can ask individuals to perform specific tasks. For example, track a dot on the screen with your eyes, read a passage that you see on the screen out loud, perform a task such as saying "patika" repeatedly, click targets on the screen using a computer mouse, and so on. And during those tasks, we can measure behavior using an array of different devices. Eye tracker to track the movement of the eyes, microphone for speech. We can measure body movement and facial expression using cameras and wearable devices. So this is one way of measuring movement. On the other hand, we can measure behavior continuously at home. So we ask individuals to wear a wrist and an ankle sensor at home continuously, and we measure whatever movements people make day to day. And these are, two very different approaches for measuring movement, and we'll talk about these different strategies over the next few slides. But we'd like to ask, which of these two approaches do you believe measures what matters most to people living with FA?
So far, the responses are pretty overwhelming for the continuous measurement at home, about 85% to about 15% task-based in clinic.
Okay. So this was kind of a wild card. I wasn't sure what to expect in terms of responses. So
Well, we're now at 90-10, so.
Okay. That's great. Okay, so I'm going to go through and go through some of the aims with digital measures. So what do we want to achieve in creating digital measures for FA? We want to have ways of obtaining reliable and objective measures of motor function. We want to be able to get those measures often, whenever we want them, and obtain them easily at home without requiring travel to a site. We like to be able to capture subtle early symptoms that are difficult to recognize in the clinic and track small changes over time, which is often challenging given that symptoms can be better or worse on a given day. We like to be able to capture symptoms in individuals who can no longer participate in some of our assessments in the clinic. And we'd like to collect data in a way both at a scale and at a resolution that allows us to train computer programs, methods in machine learning and artificial intelligence to discover new patterns of behavior in FA that can help us both measure and identify symptoms in FA even better. And those aims translate into some use cases that I'll go through here. And as we go through these, it would be great if you could choose up to 3 of these in the Poll Everywhere software. So we want digital measures to be able to help us run more efficient clinical trials. So reduce the duration, the number of participants needed, make them less expensive. This reduces burden on the FA community. It also encourages more companies to develop therapies for FA. We'd like to improve access to clinical trials, regardless of where individuals live. We'd like to expand who we can evaluate in trials. So we'd like to run trials in early stage FA and run trials in individuals who can no longer walk. Those first 4 are aims for clinical trials. We'd also like to be able to track symptoms over time at home more easily, be able to understand symptoms in real time, get information about day to day, is today a better day or a worse day? Am I at an increased risk of falls today? We'd like to be able to obtain measures that can help us understand the effects of interventions at home. Is a new diet or new therapy routine helping? And we'd also like to be able to collect objective data in the real world to help us understand, are certain medications that people are taking actually helping? And who are those medications helping? So if you can go into Poll Everywhere and select up to 3 choices about what matters most to you.
So far the top choice is really improving access to clinical trials regardless of geography. And also another top response is running trials in individuals who are no longer able to walk, tracking symptoms over time at home, understanding the effects of interventions at home. But you know, there's a good representation. Kind of all of these things are important. None of them got very low scores.
Great. And people could select up to 3 for this answer choice?
Yes. Yep.
Should we give it some more time or should we move on?
It looks like the percentages are staying pretty stable now. We can probably move on.
Okay. All right, now I'll go through and share some examples of sensor data and how we go about analyzing the data. I'll start with the task-based approach. In this particular task, a passage appears on the screen and individuals are asked to read the passage out loud. And as we read a passage, our eyes make fast movements from one part of a word to the next part of the word, and do that in sequence over the course of the line. And those fast eye movements are called saccades. If we look at the eye movements as an individual reads this passage, we can see those saccades, the eyes moving from one part of a word to the next part of another word, and do that left to right across the screen. And then make a big eye movement jump back to the next line, to the beginning of the next line, and repeat that pattern forward. So the blue line is showing the change of the position of the eyes on the screen going left to right across each of the first 5 lines of this passage. And below that, you can see the audio trace of the speech recording. So you can see the different words and syllables being uttered as the eyes are moving across the screen to read the passage. So in the top, I'm showing an individual without Friedreich's ataxia, and in the bottom, an individual with FA. And our goal is to identify differences in the pattern of speech and in eye movements that are unique to FA. And so here I'm just describing the steps that we take. We go from the original data coming off of the device, which is something like up to 1,000 samples every second, the position of the eyes, or 44,000 samples every second of the speech recording. So we go from that raw data and we use signal processing and machine learning methods to summarize these patterns in a small set of numbers. So we get in the summarized data 50 to 100 or so numbers that represent characteristics of the behavior. So what is the average size of a saccade as a person's reading the passage? What's the average and variability in the speed and the accuracy of those eye movements? We get measures, for example, the syllable rate. So how many syllables are being uttered every second as the individual's reading the passage? We can look at relationships between eye movement and speech. So for example, what's the delay between the eyes looking at a part of a word and then actually saying that word out loud? And the summarized numbers can also represent abstract features that don't map directly to characteristics of eye movement or speech, but are patterns learned by an AI system that are then useful in making predictions. For example, what is the function of the individual? So we go from the original device data to these small set of numbers that represent characteristics of the movements. And then we combine that summarized data, the characteristics of the saccades in speech, into a single measure that represents severity. So a number that represents difficulties in speech, or difficulty in controlling the movement of the eyes, or a measure of overall motor function. And the way we go between that summarized data and that outcome measure is by combining those summarized features in some way. And that can be tuned depending on what the goal is. If the goal is to measure daily function, that might be one combination of saccade and speech properties. If we want to have a measure that captures subtle changes over time, that might be a different combination of those summarized data. Okay, so if you had to choose between seeing one of these three different types of data, and I think we can select up to two, which would you like to see? If you perform this task, what data would be interesting for you to see about yourself? So we can choose between the original device data, the summarized set of features, and then the overall outcome measure.
So this is interesting. So far, we kind of have a split. Just over 50% want to see the outcome measure. But we have about a little over 10% wanting to see the original device data and about 35% the summarized data.
Okay, so most want to see the overall estimate, the outcome measure, and then the second most, pretty close to that, is the smaller set of numbers that characterize eye movements and speech.
Yes.
Great. All right. So now that was an example of a task-based digital measure. Now we're going to talk about, for the rest of this, wearable sensors worn continuously at home to characterize natural behavior. So in this plot, I'm showing what 24 hours of wearable sensor data looks like. So these wearable devices have accelerometers that measure acceleration of a wrist or an ankle in three directions during natural behavior. So the red, blue, and green lines represent acceleration in the X, Y, and Z directions over the 24-hour period. So the dotted red lines are showing when the individual is asleep, and then after those red lines shows the daytime period. And you can see this about 16 hours of daytime data shows that there's a lot of activity. But unlike the task-based approach, it's hard to look at the data from a bird's eye view and see what's actually happening. So we have to develop strategies that can analyze this continuous daily data and characterize the movements when people are doing all sorts of different things. We lose the context of what individuals are doing, but we can still find ways to understand characteristics of movement. And one way we've developed to look at that natural behavior is to analyze movement building blocks. And these movement building blocks are called submovements. In motor control theory, all complex movements, whether you're walking, whether you're eating, whether you're writing, all of those movements are composed of a smaller set of smaller movements that are combined in some way to produce that behavior. And so when we look at that continuous daily data, we work to identify those movement building blocks or submovements so that we can characterize the movement no matter what people are actually doing during the day. So let's say we have someone's reaching for a cup of water and their wrist begins at position A and makes a movement that looks like this to position B to grab the glass. If the arm's making this motion and you look at the speed of the arm as they're making that motion, it begins at rest, it increases in speed, and then decreases in speed and stops. And so this is one submovement. Now, if that reaching pattern was different and it had an oscillation that looked like this, now the movement of that limb has a different speed profile that's composed of these three smaller submovements that have a difference in the shape. And so by analyzing and identifying these submovements and quantifying their characteristics, we can measure the properties of movement during everyday life. And in this plot, I'm showing the steps in a little bit more detail. We start with that continuous daily or that continuous daytime data. We identify short periods of activity when the person is moving. These might be 10 or 15 seconds long. And from that 10 or 15-second period, we can identify what direction is the motion mostly in, and then what's the secondary direction of motion. And in that, both that primary direction and secondary direction of motion, we can identify those sub-movements that we saw earlier. I'm showing them in different colors here. And then we can quantify those sub-movements. What's their shape? What's their speed? What's the variance, moment to moment in the characteristics of those sub-movements? And we go from that raw device data, that original device data, to summarized data, which is now about 70 features that reflect the properties of those sub-movements. And then we can combine those 70 features into an overall movement score or outcome measure that we can track over time. So now I'll talk about an at-home wearable study in FA that we've been doing with Children's Hospital of Philadelphia and FARA, and Fei Yang has been leading this study. So in this study, individuals are asked to wear a wrist and ankle sensor at home continuously for a week at a time and repeat that data collection every 6 months. So far we have 35 individuals with FA and 29 controls. We have a pretty wide age range in this study. Individuals in this study so far have a range of severity. So 19 individuals use a wheelchair, 8 use a walker, 4 use a cane or a walking stick, and 4 use no assistive device. And the questions in this study are these measures, the overall outcome measures based on wearable sensor data, are they reliable? Do they reflect motor function at home? Do they capture change in FA over time? And are they relevant across different ages and severity levels in FA? So I'll show some data. So here we're looking at longitudinal data from 13 individuals with FA, where we have at least 2 time points so far. So each of these lines represents an individual, and the red lines are people with FA, and the gray lines are control participants. And this is showing the sensor score for this individual at the beginning of the study at time 0, and then the sensor score again 6 months later. And so you can see across the individuals with FA, the sensor score for most individuals is increasing slightly over time. And so this shows us that the sensor measure is able to capture changes in FA over a 6-month period. You'll also notice that the changes are small. So this is indicating that it picks up change, but it's also a reliable measure that's not dramatically changing from one time to another, which we wouldn't expect. Now we're looking at the sensor score at a moment in time in each individual with FA and in control participants. So each dot represents an individual at a 1-week period of time. And we're plotting that score as a function of the individual's age, from 3 years old to 60 years old. And we can see across the range of age of individuals with FA, there's separation between FA and control participants. When we look at the youngest individuals, we see more overlap between FA and control participants. And we're working to collect more data in young individuals so that we can tune that sensor score to best capture changes in young individuals as well. Okay, so I'm going to finish up by just describing some of our next steps, both with task-based measurement in the clinic and continuous measurement at home. And for task-based measurement, we're working to expand data collection in individuals with FA. So in the coming months, we're hoping to recruit individuals with FA to come into Boston and collect data using this task-based approach. In parallel to that, we're working to create a mobile version of NeuroBooth, of this data collection system that can be used easily at other sites, and support data collection in many individuals with FA in a relatively low burden manner without requiring too far travel. We're also on the continuous measurement at home approach, we're working to incorporate wearables into natural history studies in FA. This will help us optimize sensor scores specifically for FA. What I showed in the prior slide were scores that were trained on data from other populations, but we want to optimize those scores for FA. We want to collect more data across the breadth of FA, so more data in children and early stage individuals in particular, where we were missing data in the current study. And we'd also like to use these objective measures to collect real-world evidence on the efficacy of omaveloxolone. But we're also working to incorporate wearables in upcoming interventional trials to help evaluate effectiveness of therapies using these digital measures. All right, so I want to acknowledge the hard work by a large number of individuals who've contributed to this work. In particular, I want to thank the FA community and FARA, who have been very active collaborators in the digital measure research and have really helped move digital measures forward in FA. So thank you very much to all of you, and happy to take any questions.
So I think we have time for a few questions from the audience. If you have a question, raise your hand. We'll bring a microphone to you because we're going to need to use that so Dr. Gupta can hear your question. Just a second. Are there questions? Oh, sorry. Barbara? I can.
Hi, Nupam. It's Barbara.
Hi, Barbara.
It's great to see that you're seeing changes over time with these measures, but how do we link that to the impact on the daily experience of having FA?
Yeah, that's a great question. So, what we do with the measures, and I didn't show the plot here, but we ask individuals about their motor function using, for example, the FA Health Index. And so then we can correlate the measures that we make with the wearable sensors with patient report of function at home. So we look for relationships between what we capture from the wrist and ankle sensor and what people report about difficulties with daily life. So that's one way that we do it. What we've found is that when we correlate digital measures with self-reportive function, you get moderate correlations. They're not extremely highly correlated. We don't get correlation values of 0.9 or above. They're typically in the 0.5 to 0.7 range, which tells us that there is a relationship, but that the digital measures are capturing something a little bit different. And that's ideally what we want, because objective measures will capture something different from self-reported symptoms.
Thank you. Do we have another?
We have a question from our Zoom listeners. Is there any information or data that comes from wearable glasses that have cameras?
Oh,
Yeah, that's a great question. So glasses with cameras, the cameras can be pointed in different ways. So, you can have glasses with cameras that capture the perspective of the individual walking about in the world. And then you can have glasses with cameras that are tracking eye movements during everyday behavior. And I'm guessing you're talking about the latter one, where the camera's pointed toward the individual's eyes wearing the glasses. But feel free to correct me if I'm getting the question wrong. I think that's a great approach. It's a nice way of collecting eye movement continuously, during everyday behaviors. And that's a big question that we have. Are there differences in eye movement patterns and movement when we ask people to perform eye movement tasks like we do in the clinic, look at my nose, look at my finger, versus more natural behaviors such as reading or navigating in the real world. So I haven't seen data in FA or other ataxias with glasses being worn in the real world to track eye movements, but I think it's a promising approach.
I'm going to ask the next panel to start coming up to get ready. And if there's one more question, we can take that as well. Yep.
Thank you so much for being here. And I have to say, my 12-year-old, anytime she can do a wearable thing for a clinical trial, she thinks she's super cool. So I just have to throw that out there. This might be way out of the box, but we know that fatigue is a huge symptom in FA, and it's something that's incredibly challenging to track in a way that is measurable and can help with getting drugs approved and determining efficacy. Is there any way this technology at some point can be used to track fatigue levels, especially when we're looking at an intervention to help with fatigue?
Yeah, that's a great point. And I think that's one of the big advantages of collecting continuous data throughout the day. If we're going to rely on the natural pattern that a lot of people become more fatigued throughout the day, so the end of the day has higher level of fatigues compared to earlier in the day, the wearable sensors can help us with that question. And we've actually started to look at that right now. When we're creating an outcome, we aggregate over the whole week of data. But we can look at trends over the course of the day and see if those movement measures are changing from the morning to the night. The other approach involves, requiring participants to give us a lot of feedback on fatigue levels. And that's something that we also want to try to do in some way that's relatively low burden. Can we get real-time information about level of fatigues from the individual wearing the devices and correlate that with measures that capture fatigue, which is clearly an important aspect of the daily life of individuals with FA.
Anupam, we're going to say thank you so much. It was great to see you, and thank you for doing this work.
Thank you very much. Thanks, Barbara. Thanks, everyone.